first question is like my attendance. So everybody must scan. It's not?
I don't see a QR code anymore.
God, it means you guys have seen the answer. Oh, okay. Okay. Remember, this is similar to the kind of stuff you guys used to do in Gen Chem, right? The order of reaction. First order reaction, second order reaction, third order reaction. When a reactant A doubles, what happened to the rate of the reaction? And blah, 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 blah. You've done those kind of stuff.
How come it never shows you?
No, it will not show you the structure. It just puts the question on the option.
When you get it like right.
Oh yeah, because I didn't. Oh gosh. Yeah, because I forgot to choose the correct answer when I was building the form. Yes, yes, all the questions of today.
He's zooming on the code. Some people in the back might not be able to see.
When you zoom and it's too big, it also creates some problem. Let me see. Like that. Hmm? Well, but at least you will be able to see. You read the question on the phone, but you need to see the structure. You need to see the answer?
There it is.
So this is an SN2 reaction, right? So here we're dealing with an SN2 reaction. Meaning of an SN2, if you recall, we said it is SN2 because it depends on the concentration of the alkyl halides and on the concentration of the nucleophile. Okay? It depends on those two concentrations. And if it depends on those two concentrations, let's call this guy A. Oh, no, what is that pen? Oh, God. I don't know. This pen is not writing. I hate to use a PowerPoint with this thing. So if this is A, if this is reagent A, and then let's call the methoxide CH3O minus reagent B, okay? The rate of this reaction is proportional to the concentration of A and the concentration of B. That's basically what this SN2 means. A is the alkyl halide, B is the base, okay? So the rate of reaction depends on that. What's the order of this reaction? This is a second order reaction. If you remember, Gen Chem, this is a second order reaction. That's why it's called SN2. Bimolecular, it means it's a second order reaction. And so if a second order reaction, it depends on the concentration of A and the concentration of B. For a second order reaction, if you double the reactant, the reaction quadruples. It increases by fourfold. Does that make sense? For a first order reaction, if you double the reactant, the reactions double. For a second order, if you double, it quadruples. For a third order, if you double, what happens for a third order? Ninefold. Right? It increases by ninefold. For a third order reaction. So in this case, the reaction will quadruple. Does that make sense? So that's basically what we learn in Gen Chem. Because it's a second order reaction. Next one. Does it scan? Yes, it does. Okay. So what's the answer? I don't have the answer. I didn't put the answer there, so you guys will not be able to see the correct answer. So which of the following factors favor an SN2 reaction with a negatively charged nucleophile? Okay, with a negatively charged nucleophile. Of course, if you have a good leaving group, then the SN2 reaction is favored, irrespective of the nature of the nucleophile. Whether you have a bad nucleophile or a negatively charged nucleophile, so long as the leaving group is good, that will favor the SN2. Okay? Now, a negatively charged nucleophile, because of that negative charge, is automatically a good nucleophile. Does that make sense? So remember last time we said negatively charged nucleophile are stronger bases than neutral. Okay? So that's a good nucleophile. Now, for an SN2 reaction, because it's a backside attack, it will prefer to have molecules that are not sterically hindered. Because it's a backside attack. If the molecule is sterically hindered, it will not be able to approach from the back. Does that make sense? So, an unsterically hindered molecule reaction center is favored with an SN2 reaction. Does that make sense? Now, because the nucleophile is negatively charged, you want to use an aprotic solvent. Because if you use a protic solvent, it will create what we call solvolysis. It will form ion dipole interaction with the solvent. It will form ion dipole interaction with the solvent and stop that nucleophile from reacting. So you want to use an aprotic solvent to do that. So in conclusion, all of the above will favor an SN2 if the nucleophile is negatively charged. The answer is all of the above. Now, if the nucleophile is neutral, if we have a neutral nucleophile instead of being negatively charged, the only thing that will change here will be D. For a neutral nucleophile, you want to have a protic solvent. Okay, a protic solvent will be good too. Well, because at least it can still go. The protic solvent will not solvate it as it will do for a negatively charged. That's my next question for today. For this one, you guys need to know the structure. So that's where nomenclature comes in. Zuri, what's the answer? Do you have any idea? Just guess. Just give any letter. What? Which one?
Benzyl bromide.
Okay, I will accept that one. Did you just guess or you knew it?
I knew because like benzyls are more stable than alcohols or cyclohexanes.
The answer is correct, but explanation I still have some, yes, glitch in there. Let's draw the structure. Do you know how vinyl bromide look like? This is a hydrogen. That would probably be a hydrogen. That's why I hate to use PowerPoint to do this. I will go back. I will return to the other one. That would be a vinyl bromide. A bromine directly connected on the double bond. Okay, that would be the structure for A. The structure for B, cyclohexyl bromide. Okay, that's the structure for B. C, phenyl iodide. Well, don't worry if you don't know this structure. In the exam, I will not just give the name. Sometimes the complicated one, I will give the structures. Yes, that will be the phenyl iodide. But it's 2-bromopropane. You guys know that one, right? You know that one. It's an easy one. That will be the structure for 2-bromopropane. And then the last one is benzyl bromide. Now that you have the structures, can we decide? This is A, B, C, D, E. Now that we have the structure, can we decide on which one now? Yes. We know it's E, but I didn't like the explanation. But now we have the structure. Can we guess why E is the correct answer? Can anyone guess why E is the correct answer? I will emphasize that we're looking at an SN2 reaction. I will emphasize that we're looking at an SN2 reaction. What kind of alkyl halide is favored by an SN2 reaction? Say that again. Primary alkyl halides are favored in SN2. So which of them is a primary alkyl halide? That's simply the question. Does that make sense? Which of them is a primary alkyl halide? The only one is E. The only one there that is primary is E. Okay, if you look at D, that's a secondary. Yes, secondary can also undergo SN2, but it will be slower. It will be slower compared to a primary. Remember, SN2 is faster with the primary and then slower with the secondary and doesn't even happen with the tertiary. Does that make sense? B is also a secondary. As for A and C, it will never happen because those are sp2 carbons. The bromines are connected to sp2 carbons. So those sp2 carbons will not undergo an SN2. Does that make sense, guys? Yes, let's get back into business now. Let's do the real business. So today we'll be talking about SN1 reaction. We'll be looking at SN1. Substitution nucleophilic unimolecular, meaning that we only have one intermediate in there. See, I was revising my slide before I came. That's why I still have to move back to where we have to go. Yes, almost. Almost. Yes. So we talked about the SN2, okay? And I said with SN2, what you guys need to remember is that primary alkyl halide react faster, then followed by secondary alkyl halide, and tertiary alkyl halide don't react at all. The nature of the leaving group is important, okay? The better the leaving group, the faster the reaction. And iodide are better leaving group than bromide, better than chloride, better than fluoride, okay? And the reason is simple, because iodide are more stable. When they will react, they will form a more stable I- ion, okay? Now, you also need to know the effect of the solvent. There are two types of solvent that we're looking here. We're looking at protic solvent and we're looking at aprotic polar solvent. Which solvent favors which condition is important. If your nucleophile is negatively charged, aprotic solvent will be good to carry out the reaction, because aprotic solvent will not enable strong ion dipole interaction to take place. Okay? Then you need to know the stereochemistry of an SN2 reaction. SN2 reaction usually takes place with a reversal of stereochemistry. Meaning if you start with a reagent that is having, for example, the S configuration, your final product will have the R configuration. There's a complete reversal of configuration. And that reversal of configuration is simply because the nucleophile is attacking the central carbon or the reaction center from the back. That's why there's that reversal of configuration. That's basically what I need you guys to know about SN2 and be able to put that in practice. So now we're looking at another type of reaction. We said tertiary alkyl halide cannot react through SN2. It doesn't mean that they don't react at all. Okay? From observation, if you have a tertiary alkyl halide, you give that under certain reaction condition, they actually react. A substitution reaction also takes place. And that substitution reaction is pretty fast. Okay? And because that reaction takes place, and we all know that tertiary alkyl halide doesn't undergo SN2, it means that there is another mechanism that the tertiary alkyl halide uses in order to react. Does that make sense? And we need to elucidate what that mechanism is. And this also happens even if your leaving group is not that good. That reaction still takes place. Now, remember, to study the reaction mechanism, it's always interesting to look at the kinetics of the reaction. What are the factors that favors the reaction, that causes the reaction to move faster or slower? And it turned out that the rate law for this kind of reaction is proportional to the concentration of the alkyl halide. Take note. It's only proportional to the concentration of the alkyl halide. Whereas for the SN2, it was proportional to the concentration of the alkyl halide and that of the nucleophile. So here, it only depends on one thing, the alkyl halide. So the nucleophile doesn't matter. So even if you like, you dump in as much nucleophile as you want, that will not affect how fast this reaction will take place. Yes?
So if you double the alkyl halide, will it just double the rate?
It will just double the rate. If I double the alkyl halide here, the rate will only double. Does that make sense? Double the alkyl halide, the rates double. So because the reaction depends only on the alkyl halide, it is a unimolecular reaction. It means that the rate determining step of this reaction is a function of the alkyl halide. It depends on one stop. That's why we refer to those reactions as SN1, substitution unimolecular. Okay, now based on that, any questions so far with SN1? That life is easy, right? Yeah. Now, in most SN1 reaction, the solvent that you use is a nucleophile. Remember, because the solvent also can act as a nucleophile even in the SN2. But the nature of the solvent also matters. So here, well, no matter the kind of solvent you use, what kind of solvent is this? Methanol, CH3. Is that a protic polar solvent or an aprotic polar solvent? Which one is that? So it's a protic polar solvent, okay? So this is a protic polar solvent. It's a good nucleophile for an SN1 reaction. Okay, so in this case, we're using methanol to replace the bromine. We're using methanol to replace the bromine. So the mechanism of the SN1 reaction is a two-step mechanism, basically. Basically, it's a two-step mechanism. The first step of the mechanism is the formation of the carbocation. Hey, see here. To form the carbocation, right? Yeah. So the formation of these, the first step of this reaction is the formation of the carbocation. You notice this is not the first time we're seeing a reaction mechanism that goes through carbocation formation. Okay, so we have a formation of the carbocation, and that formation of the carbocation is our slowest step. So that's the rate determining step. So if I ask you guys to sketch the reaction coordinate for this, that step will have a high activation energy. Does that make sense? That will be the step with the highest activation energy because that's the slowest step of the reaction, the formation of the carbocation. And so once your carbocation is formed, the rest of the mechanism is exactly similar to the acid catalyzed mechanism that we did in the chemistry of alkenes. Does that make sense? The rest of the mechanism is similar. Your nucleophile attacks the carbocation, and then deprotonation takes place, then you have your product. Question. There's no way I can really make this bigger so that everything comes out. Question. Yes.
How can you tell if it's fast or slow again?
The slowest step is always the formation of the carbocation. That's the slowest step, okay? Yes. In all the mechanisms that we've been doing, even in the chemistry of alkene, if that involves the formation of the carbocation, then that will most likely be our slowest step. Okay? I uploaded the video last night. Question, guys, or remark? Any remark or any question? Idea? There was no traffic today. Yes, I'm just reminding you. Okay. Any observation? It's a carbocation, right? So everything we said about the carbocation when we're talking on the chemistry of alkene is true for this one. Does that make sense? Everything we said about carbocation in the chemistry of alkene is true. And what do we say about carbocation in the chemistry of alkene? Guys, we're having a test in 1 week. Huh? What do you guys know about carbocations, guys? And carbocations. Say that again. That's what. Say that again.
They form a racemate mixture.
Okay, any reaction involving carbocation, I said it in this class. If in terms of stereochemistry, your product will end up being a mixture of R and S. That's what we call the racemate mixture. Does that make sense? That's what we said about carbocations when we're doing the chemistry of alkene. What else do we talk about carbocations? What else can happen when you have a carbocation? Rearrangement, thank you. You can have a rearrangement when you're looking at carbocation. You can have the 1,2 hydride shift, you can have the 1,2 methyl shift. And you guys remember the condition when you can have a hydride shift. If your carbocation is next to a tertiary center, then you will have a hydride shift. If your carbocation is next to a quaternary center, then you will have a methyl shift. So all those things is true. Whenever you form a carbocation, that is true. Does that make sense? And each time you form a carbocation, take some time and observe that carbocation and ask yourself the question, will this carbocation undergo a rearrangement? If the answer is yes, then do it. Does that make sense? So everything we said about carbocation is true. I will repeat, it's true. And now that also makes sense why tertiary alkyl halide prefer to go through SN1. They prefer to go through SN1 because they know that they will form a stable intermediate. They will form a stable carbocation. Does that make sense? So you notice the difference in stereochemistry between the SN1 and the SN2. The SN1 will form a racemic mixture because you are going through a carbocation, whereas the SN2 will always give you a reversal of stereochemistry. It will always give you a product whose stereochemistry is the opposite of that of the reactant. That the SN2 will always give you a product whose stereochemistry is opposite to that of the reactant. So like I said, if I ask you guys to draw the reaction coordinate diagram for this reaction, okay, I know that the reaction is a 3-step mechanism. Those are the 3 steps, or we have 3 transition states, because I can see them here. These are the 3 transition states over here. And like I said, the first step, which is the formation of the carbocation, will have the highest activation energy. The first step, formation of the carbocation, will have the highest activation energy. Here, that step. You see the activation energy is high. That's why it's called the rate determining step. Then the other step now will progressively have lower activation energies. Does that make sense? You should be able to sketch this kind of diagram. I expect you guys to be able to sketch that. Now take note, sometimes secondary alkyl halide can also undergo SN1, okay? Sometimes it can also undergo SN1, but it will preferably undergo SN2 over SN1. So in terms of the stereochemistry, just like we discussed, they say the product is a pair of enantiomer, meaning a mixture of enantiomers. So if you have a tertiary alkyl halide, like what we have over here, and that tertiary alkyl halide undergoes an SN1, you will form 2 products. One will most likely be the R, and then the other one will most likely be the S. So you form those 2 products. That's what we refer to as the race mix. So they mix them out. And you know why? Because the carbocation, the carbon atom has an sp2 configuration or hybridization. And being sp2, it is trigonal planar. If it is planar, it means that the nucleophile can attack from above or from below equally. That's why you end up forming a race mate. Does that make sense? So you end up forming a pair of enantiomers. One will be R, one will be S. And if those pair of enantiomers are present in equal proportion, that's what we refer to as race mate. Does that make sense? If they are present in equal proportion, then we refer to that as a racemate. This diagram basically explains what that racemarization is all about. When you have the carbocation here, this is the carbocation. That carbocation is flat. So, your incoming nucleophile can attack it from the B side, or it can attack it from the A side. If he attacks from the A side, you end up having that product. Okay? If he attacks from the B side, then you end up having this other product. I don't know, one of them will be R, one of them will be S. That's how you form those two products. So if in class I ask you a question and I want the stereochemistry, you need to tell me that it will either give you racemate or something else, you know. You must give me that stereochemistry. It's important. Now, in nature, most of the SN1 reaction actually leads to a partial racemarization. You know what racemarization is? Equal mixture of R and S. But in this case, it turned out that sometimes you might have more of the S being produced compared to the R, or more of the R being produced compared to the S, okay? Sometimes, that's a general observation. An explanation to that, if you look at the mechanism, we can have a clear explanation to why it sometimes happens. It has to do with the leaving group. It has to do with the leaving group. Think about the mechanism of an SN1. You have a leaving group. The leaving group has to leave, detach from the carbon first, completely, for the nucleophile to come in. Okay? Now, if the leaving group is slow in detaching from that carbon, you see that technically he's blocking already one side of the carbon and then favoring the other side. I don't know if you understand what I'm saying here. Okay, if that detachment is slow, the leaving group is blocking one face of the carbon and then leaving the other face open. So that's why the other phase, the product due to the other phase, might be in higher amount. But if your leaving group is fast in leaving, if he leaves very fast and then leaves those phases open, equal chances, then you will end up having a perfect racemarization. Does that make sense? So that's why we say here, we refer to that as a diffusion. Yes, Vicky. Well, usually we just know that by observation of the product. Like if you run an SN1 reaction and you realize that your product is not like a perfect racemarization, then that's most likely the explanation you will provide. Does that make sense? Yes. And so in this case, that's why here, if you read here, that's why it says here in English, not in Homala. Who wanted me to speak Homala again? Okay, so that's why we say here that if the BR has not diffused away, meaning that the BR didn't go away completely, you see that this route is already blocked because the BR is still standing around there. So that road is blocked, and then it gives room only for the nucleophile to attack from behind. Does that make sense? But then, if you have a situation where your nucleophile completely leaves, it gives an equal chances, and that's why you can have a perfect racemarization. Drink coffee. If you drink coffee, that will be very useful. Trust me. Yeah. So that's a summary. You guys should read that while I'm taking some break. That's a summary for the SN1 and the SN2 or whatsoever. The rate of the reaction depends only on the constitution. The archivalite, tertiary archivalite, the not primary and secondary archivalite undergo SN1. If the halogen is attached to an asymmetric carbon center, the product will be a pair of enantiomers. Right? That's just a good summary of that. Now let's talk about the leaving group. The leaving group here is exactly the same as what we did for SN2, okay? If you have a weak base, then that would be a great leaving group. And so the iodide is a good leaving group compared to the fluoride, which is the same story we had with the SN2. With the SN2, the iodide also was a better leaving group compared to the fluoride. Is that okay? So we have a table here. We'll not be able to read through it in detail, but it makes a quick comparison between the SN1 and the SN2. In terms of mechanism, the SN2 is a one-step mechanism, meaning that you only have one transition state, whereas the SN1 at least is a two-step mechanism. One is bimolecular, the other one is unimolecular, the rate determining step. In terms of stereochemistry, for the SN2, we always have that inversion of configuration, whereas for the SN1, we can have retention. We will have retention and inversion. So that's what we call a race mate. For the SN2, in terms of the leading group, the iodide is better than the fluoride, which is the same thing for the SN1, where the iodide is better than the fluoride. Okay? And tertiary alkyl halides we prefer to go through SN1, whereas primary and secondary prefer to go through SN2. So that's basically a summary comparison between the SN1 and the SN2. You guys have the slides. The slides are on your blackboard, right? I think I uploaded everything on blackboard. This is the first time at least I'm on time. I uploaded it since the beginning of the semester. So we are done with the substitution reaction. We are done with substitution reaction. So if we have an alkyl halide, remember this slide. We talked about this slide at the beginning of the class last Tuesday. We said two things can happen when you have this. You can have a substitution reaction and you can have an elimination reaction. And in terms of substitution reaction we just covered, it can proceed through two types of mechanism. The substitution can go through an SN2 or it can go through an SN1. Hey, notice the way I write my SN1. You see the N is kind of like underscript. Yes, it's important. That's the way the convention is. So those are the substitution, and we've talked about that. Now, sometimes, under certain reaction condition, instead of undergoing a substitution, it will undergo an elimination. And just like substitution, there are two mechanisms for the elimination. It can go through an E2 or it can go through an E1. Elimination bimolecular, elimination unimolecular. Okay, and so that's what we have to do. That's what is left for us to finish this. You can already guess, right? You guys can guess. E1 is similar to SN1. E2 is similar to SN2. What do I mean by similar to SN2? E1 in terms of the mechanism, we're just making like no similarity. SN1, the mechanism goes through the formation of a carbocation, right? So do E1. E1 also goes through the formation of a carbocation. Does that make sense? SN2 is a one-step mechanism. So is E2. E2 is a one-step mechanism. You can start seeing what I'm seeing. Can someone see what I'm seeing? Can someone see what I'm seeing? No, no, keys. I know you can see what I'm saying. Maurice, can you see what I'm saying, or do you know what is in my mind? Tell me that you are not a sorcerer.
Is it elimination as a double bond in the product?
Yeah, well, the product will be a double bond. Yeah, I said SN1 is very similar to E1, but they end up giving different product. But they are similar in their mechanism because they all go through a carbocation. Then SN2 is very similar to an E2. It's a one-step mechanism, but they all give you different products. So what's the problem? What do you think can be the problem? I'm put it in a nice way. What can be the problem here? Look at this guy. It's the same guy. The same guy can go substitution, can go elimination. What will be the problem? There will be what? There will be a competition. Does that make sense? There will be a competition. We need to decide what will go. Will he go through as a substitution, or will he go through an elimination? And then remember, we said, what kind of reactions are favored by SN2? What kind of alkyl halide? Primary and secondary. Those same alkyl halide, primary and secondary, also are favored for the E2. And so you notice that an E2 reaction now will be in competition with an SN2. Tertiary are very good for SN1. So tertiary are also good for E1. And so you have a competition between an SN1 and an E1. Does that make sense? There will be that competition. There will be that competition. Yes. That will be our job. Yes. Our job is to play the referee, okay? That will be our job, to determine the conditions for those competition. So, just like I said, remember, just like I said, the E2 is very similar to the SN2. It means that the rate law are the same. You remember that for the SN2, we said the rate law depends on the alkyl halide and the nucleophile. E2, because the guy doesn't want to use the name nucleophile, he decided to call himself a base. So they will say the rate depends on the alkyl halide and the base. Does that make sense? You see, they are twins, but they don't like each other. Yeah, they are twins, but they don't like each other. So instead of calling himself nucleophile, the guy said, no, I'd rather call myself a base. I'd rather call myself a base. Now, in this case, that's what the reaction will be. We'll get into more detail. So this you already know. So it means that if we double the concentration of the alkyl halide and double the concentration of the base, what happens? Okay, does that make sense? If we double the alkyl halide and double the base, the rate will quadruple. Those are the kinds of stuff I want you guys to keep in mind. Now, the mechanism here, I said it's a one-step mechanism. It's a one-step mechanism. Your product, you're forming a double bond. There are two kinds of carbon atoms of interest here. There are two kinds of carbon atom of interest. There's what we refer to as the alpha carbon, which you already know, right? The alpha carbon is that carbon, in this case, that bears a functional group. The functional group is Br. And so the carbon atom that bears that functional group is what we refer to as the alpha carbon. And then the carbon following the alpha carbons, we refer to them as the beta carbon. Does that make sense? So an E2 can also be referred to as a beta elimination. So if you go somewhere, some people may refer to it as a beta elimination. And it's simply referred to as a beta elimination because you are removing one hydrogen from the beta carbon and the functional group of the alpha carbon. Does that make sense? That's what elimination is all about. You're removing a hydrogen atom from the beta carbon and the functional group. And everything is taking place in one step. The one connected to the alpha carbon. Does that make sense? Everything takes place in one step. The base, because it's a base, will abstract the hydrogen atom so it gets that hydrogen, and the electrons that forms a bond between the hydrogen and the carbon will now collapse to create a double bond over there. Once it does that, it kicks the leaving group out. That's the mechanism. Everything in one step. And then you form your alkene, and you form your base, whatsoever, your leaving group and your water molecule. Okay? It's a one-step mechanism. Everything takes place at once. Question? Well, this molecule will, this is a tertiary alkyl halide actually. Here. Yes, that's why they are all connected to the alpha carbon. So just like I said, the halogen comes from the alpha carbon, the hydrogen comes from the beta carbon. Okay, we talked about that already. So, yes, that's it. And the name of this reaction is called dehydrohalogenation. Okay, that's how we'll refer to this reaction. As from today, we'll baptize you dehydrohalogenation. And the name means a lot. The D is kind of like eliminating, removing. If I say dehydration, it means I'm removing water. Okay? Now, dehydro, that hydro is the hydrogen. Does that make sense? That hydro stands for the hydrogen, and then halogenation is this halogen. So D, I am removing a hydrogen and a halogen. That's what it means. Dehydrohalogenation. I am removing a hydrogen and a halogen. That's the name of the reaction. Okay? Dehydrohalogenation. E2 reactions are radioselective. You remember what radioselective is? Radioselectivity. We said in radioselectivity, if you have a possibility of forming two isomers, you preferentially form one over the other. That's what we refer to as radioselectivity. Does that make sense? If you can form two constitutional isomers, but you can preferentially form one constitutional isomer over the other one, then we say that reaction is radioselective. And E2 are radioselective. Let me zoom it so that we can appreciate it more. So this is our base, the methoxide. Jasmine, where's Tyler? So look at this reaction. That's our base. This is our halogen, the halogen that will be eliminated, right? And then in this case, we have two beta carbons. Remember that the hydrogen is coming off of the beta carbon. Now you have two beta carbons, and those beta carbons are not the same. They are not the same type of beta carbon. One of the beta carbon is an alpha carbon, or it's a primary carbon. The other, this guy, is a primary carbon, and this other beta carbon is a secondary carbon. So they are not the same. Okay, one of them will be preferentially used over the other. Does that make sense? So between these two beta carbons, one of them will be used over the other. And that will now depend on the one that will lead to the formation of the more stable product. Does that make sense? Because things react because they want to attain stability. And so The beta carbon that would lead to the formation of a more stable product will be the major product. Does that make sense? That's called the ZF rule, and we'll talk about it in detail. Hey God, this thing wants to go off. ZF's rule. This laptop should better stay alive, else you guys will leave early. So, if you have those beta carbon, if you remove those beta carbon, these are the two products that you can form. You can form 2-butene, you can form 1-butene. Okay? And in this case, 2-butene will be the major product. And the reason is simply because that's the more stable alkene. Remember, stability of alkene, the more substituted the carbons involved in the formation of the double bond are, the more stable they are. And so here you have a greater substitution compared to here. In other words, you can also look at the number of hydrogen. The fewer the number of hydrogen involved in the double bond, the more stable that alkene is. And so here I only have 2 hydrogens that are surrounding my double bond versus 3 hydrogens surrounding the double bond. So the fewer the number of hydrogen, the more stable the alkane is. That's what we call the ZF rule. Okay? I don't know why they keep giving rules in chemistry. So in that case, is the removal, in that case, it will be the removal of that hydrogen. So if you remove that hydrogen, then you will form your more stable product. Yes.
You said the amount of hydrogens around the carbon. Are you talking about which carbon are you talking about?
The sp2 carbon, the carbon involved in the formation of the double bond.
Okay. Okay, both of them or just one?
Both. Okay. Total number of hydrogen. So does that make sense with radioselectivity? So your major product will always be the one that will give you the more stable alkene. But in life, there is no rule without exception. Right, Andre? There's always exceptions. Sometimes you told me that let the exception be the rule and the rule be the exception, right? That's what is happening in chemistry here. That's what is happening in chemistry here. So the next slide will basically explain why the more stable alkene will be the major product. So I won't spend too much time on that one, on that detail, because it forms a more stable transition state. Remember, I said if the transition state is lower, it means the reaction will be faster. And so the guy that leads to the formation of the more stable alkene will have a lower transition state. And so that reaction will be the one that will proceed faster. Is that okay? That's the one that will proceed faster. And over here, we just have a picture of what those transition states look like. That will be the transition state diagram for the more stable, and that will be the transition state diagram from the least stable. It's just for your appreciation. Yes, I will never ask you guys to draw that. Yes. The one that leads to the most stable product react faster because the transition state is more stable also. So this is just an emphasis of what we've been saying. All these reactions, they are just emphasis of what we've been saying. Okay? If you look at this other reaction, that's my chlorine, that will be the leading group. And then we have the 2 beta carbon. So one of them will take up the hydrogen. If you choose to remove this hydrogen over here, that will lead to the formation of this product here. Okay? If you choose to remove this other hydrogen, that will lead to the formation of this product. And this product is more substituted than this other one. So this is a more stable product. That's just an emphasis of what we've been saying. It's the same story over there. If you look at that, it's the same story. You have your leaving group here, and these are the 2 beta carbons. You can either remove this hydrogen or remove that hydrogen. Okay? If you remove this hydrogen, you form the more stable product. If you remove that hydrogen, you form the other product, which is relatively less stable. Okay? That's just an application of what we've been saying so far. That's the radiochemistry. That's the radiochemistry. And I told you guys that that rule is referred to as the Zetev's rule or Zaitev's rule. That guy should be Russian. He should be a Russian. But just like I told you guys, in life, there are some people that don't like to follow the rule. When you lay down some rules, then they will say, no, I will do what I know or what I want. So there are some molecules that don't follow the Zetev's rule, meaning that the product is not necessarily the most stable alkene. Okay? It means that the product is not necessarily the most stable alkene in the sense that we know. Let me put it that way. In the sense that we know. In the sense that we know, what does that mean? That the more stable alkene will be the most substituted one. That's what we've known, right? But in this case, if your product can lead to the formation of a conjugated alkene, meaning double, single, double bond, usually those conjugated alkenes are even more stable than the ones that we know. And so it will prefer to form a conjugated alkene, meaning a double, single, double bond, as opposed to forming an isolated alkene. This is called isolated alkene because you have a double bond and then single, single, then a double bond. That's the meaning of isolated alkene. Conjugated alkene means you have an alternation of double and single bond. Okay, and those guys are more stable than whatever type of alkenes you know. The ones that lead to that conjugation, they are more stable. Yes.
So conjugated, you said it's double, single, double?
Yes, that alternation of double, single, double. Okay. Now, isolation is when you have that break in that alternation. So if I have double, double, then, that's not conjugated. If I have double, single, 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 double, no, that's not conjugated. Does that make sense? And conjugated alkene are more stable than whatever kind of alkene you know. And the reason is easy, because of resonance. The more conjugation you can do, the more resonance structure you will have. Does that make sense? The more conjugation, the more resonance structure. And so the ones that will lead to a product that will form conjugation, they will not obey the Zetev rule, which is the same story here. Here, this product is measured because you have this double bond, single bond, double bond, single, double, single, double, single. So you see, it leads to a conjugation. Whereas here, it leads to an isolation because it gives you a double, a single, a single. Does that make sense? So the ones that lead to a conjugation will always give you a more stable product. I know it's a lot of information. I know it's a lot of information. It's not my fault. It's chemistry's fault. Samantha White is not in class. A lot of people are not in class. Yeah. Huh? Another limitation to the Zetev rule is the size of the base. If you have a bulky base, okay, if you have a bulky base, there will be a problem of accessibility. Okay, for example, let me zoom it. Here, this is our living group. This is a beta carbon, and this is another beta carbon. Does that make sense? Those are the two beta carbons. And so one of those hydrogens need to leave. We need to remove one of those hydrogens. Is that okay? We need to remove one of them. Either this one or that one. But then if you have a bulky base, like this guy, is bulky, it will be hard for that bulky base to access this hydrogen here. So those who will be watching the video will not even know what I'm talking about. It will be hard for the bulky base to access this hydrogen. It will be hard because the hydrogen is kind of hindered. Does that make sense? And so the bulky base will go for the one that is easily accessible. It will attack either this one or that one. And by attacking those one, it will not lead to the kind of product we expect. Because these are the two products. Although this one is less stable, but it will be our major. And then our more stable becomes the minor. Simply because we had a bulky base that could not access the beta hydrogen of interest. Does that make sense? But if you have a small base, then the rule will apply. Is that okay? The size is also important. So I think those are the two limitations to the ZF rule. So the first limitation is if you lead to the formation of a conjugated system, then that hydrogen will be preferentially taken over the one that will produce a more substituted alkene. And then the second rule is the base, the size of the base. The more bulky the base is, then chances are that will not obey the ZF rule. Okay. And so that's a table that gives you a summary of the size of the base. The size of the base. You notice that when we have a smaller base, when we have a small base here, when we have a small base, the more stable alkene is our major product. But when we increase in size of the base, the more stable alkene now becomes a minor product. Does that make sense? That's just a table summarizing what we've been doing. When you have a small base, the more stable alkene is the major. But when the size of the base increases, the more stable becomes the minor. Here, on this table. This is our base. That's a small base. If it is a small base, the more stable alkene is the major product. That's why we have 79%. Okay? But when we increase in size of the base, just like what we have down here, the base is getting bigger. As the base gets bigger, you can notice that the amount of the more stable alkene decreases. Yes, in the lab. So, and those were the observed. Those are the percent yield values. Those percentages are the percent yield values. Question. So we'll most likely finish this chapter on Tuesday. And then on Thursday morning, we'll have a review session on Thursday morning. Technically, the review session of Thursday morning is not a review per se, because by then you should be kind of ready to take the exam. So it will be more of question and answer session, clearing out the doubt that you guys have. That's what Thursday morning will be. Then during my lab session on Thursday again, it will be another opportunity for answering questions. Then we'll meet on Thursday 6:30 for the exam. Yes. I'm still thinking of what kind of exam question I will ask you guys. But it will be from your textbook. Okay? It will be from your textbook. Chapter 5, chapter 6, chapter 9. At least the question that will be from me. The questions that will be from me will be from your textbook.